So now we're going to make the connection between electromagnetic radiation and one of our more modern understandings of the atom. After we discovered the nucleus, the electrons were really a mystery that people wanted to solve. It didn't seem to make any sense that they're negative and protons are positive, but the electrons aren't stuck into the nucleus. Okay, we knew that they existed outside of the nucleus, and we knew that they were moving around, but we really didn't understand a lot about them. Until this guy, Niels Bohr, came along and made kind of a startling connection between radiation and electron arrangement. So this image right here is the full spectrum of the rainbow if you're looking at all the colors. And what he was able to put together is that if you heat up elements, they give off certain parts of the spectrum, okay, but not the whole spectrum, just very, very specific wavelengths of light. So the connection that he made was these wavelengths are created by electrons. If we know that colors are associated with energy and that these electrons are making different colors, then that means that the electrons themselves must be positioned in a way that gives them different amounts of energy. So through some very complicated math, he was able to put together kind of this basic diagram of the atom. So we have this purple dot right here in the middle, that's supposed to be the nucleus, and he summarized that there are 7 possible energy levels that the electrons can exist on. And on level 1, we can only have 2 electrons. On level 2, we can have 8. On level 3, we can have 8. On level 4, you can have 18, level 5, you can have 18, level 6, you can have 32, and then level 7 is another 32. So it kind of makes sense that as the rings get bigger, you get more and more and more possible electrons that can exist on those energy levels. So they represent increasing energy. So the electrons that are on level 1 are going to be our lowest energy electrons, and the electrons on level 7 are going to be associated with really high energy. In order to draw a Bohr model, you really just have to know the rules. You have to know how many total electrons, and then you need to remember that the first ring fills with 2, the second and third ring fill with 8, etc. So if we start with hydrogen, hydrogen only has 1 electron. So the very first energy level, you put 1 dot on it, and there's your Bohr model for hydrogen. If you're looking at lithium, you have to have 3 electrons altogether. So lithium will use the symbol to represent the nucleus. The first energy level has 2 dots, which means that, and that's full. So that means that we need to add the second ring and put that last electron on the second ring. If we're filling out the diagram for oxygen, we need to have 8 electrons altogether. So the first ring has 2 electrons, and the second ring would have 6, 3, 4, 5, 1, 2, 3, 4, 5, 6, 6 altogether. So there's your Bohr model. Sodium, has 11 electrons altogether. So Na, first ring has 2, second ring 1, 2, 3, 4, 5, 6, 7, 8. So the problem with the second ring is when we get to 8, that means it's full, but this is only 10 electrons, so we still have 1, which means that we're going to have to add the third ring and put 1 valence electron out on the outside. Aluminum, needs to have 13 electrons. So first ring 2, second ring's going to have 8, 2, 4, 6, 8. And then that means the third ring would have the last 3. Argon. So argon has 2, and then it would have 8, 4, 6, 8. And then, in order to get all 18, we have to have 1, 2, 3, 4, 5, 6, 7, 8. And lastly, we'll do calcium here, which needs to have 20. So the first ring would have 2, the second ring would have 1, 2, 3, 4, 5, 6, 7, 8. And then that means the third ring would have 1, 2, 3, 4, 5, 6, 7, 8. So this is only 18 altogether. So we're going to add that fourth ring, and we're going to put 2 more electrons on it. And I'm going to do 1 more, just because I'm going to use it later as an example. So phosphorus needs to have 15 altogether, 2 on the first. We can fill up the second one with 8. So that's 10. So that means the third one can have 5. So what's really cool about what Bohr discovered is that the periodic table was already arranged based on properties. So metals become positively charged, nonmetals become negatively charged, and some are +1, some are -2, whatever. Okay, but when he did his math and he made his predictions about rings and how many electrons can go on each one, it started to correlate with what was already known about the periodic table. So if you remember, there were 7 rings that Bohr said could be on the periodic table. There are 7 periods. Okay, if we look back, okay, and look at hydrogen. Okay, hydrogen is on the first period on the periodic table, and it has 1 energy level. It's also in group 1A and has 1 electron on the outside. So if we look at lithium, okay, the difference between hydrogen and lithium is in period 2, which is why it has 2 energy levels, but it is still in group 1A. So even though there are 2 on the inside, there's 1 electron on the outside. If we look at oxygen, okay, second period again, but this time we are in group 6A. So if you have 2 energy rings and you're in group 6A, you should have 1, 2, 3, 4, 5, 6 electrons on the outside. So sodium, period 3, 3 rings, back to group 1A, 1 electron. Phosphorus is also period 3, so it has 1, 2, 3 rings, and it is in group 5A, so it has 5 outside electrons. And then lastly, we'll look at calcium. It's in the 4th period. It has 4 rings in group 2A, so it has 2 electrons on the outside. So what we're going to start to realize here is these outside electrons are kind of a big deal. They sort of are the electron that determines everything about the element. So for example, hydrogen's in group 1, which means we know it makes a +1 charge when it becomes charged. Okay, the outside of the atom is what's exposed to the environment. So if +1 means we're going to lose an electron, we're going to lose an electron from this outside ring. If we're looking at lithium, lithium is in the same situation as hydrogen. It always makes a +1 charge, which means it usually loses an electron. And because level 2 is exposed to the outside world, it's going to lose the electron that's on the outside. The term for these outside electrons is valence. So the valence energy level is the ring that the electrons are on, and then the electrons themselves are called valence electrons. So if we look at, let's look at phosphorus again. Go back to phosphorus. Okay, so the valence shell is level 3, and there are 5 valence electrons. So we talked earlier that level 3 fills up with 8 electrons. Okay, we know that phosphorus usually makes a -3 charge. Okay, well, level 3 as it is now already has 5 electrons on it, which means that it only has 3 empty spots that can be filled by an electron. That's the reason why phosphorus makes a -3. Okay, if it's going to gain electrons, it's going to gain exactly 3 so that it can fill out the 3rd ring, and it's going to stop at 3 because the 3rd ring can't have more than 8. Calcium has the opposite problem. So level 4 can go all the way up to 18, and it only has 2 valence electrons. So calcium always makes a +2 charge, because if we drop these electrons, the 3rd level that lies beneath has been filled with 8, and that's what stabilizes the atom and makes calcium happy. So the reason why Bohr was able to make this discovery is that electrons are not stationary. They move around a lot. And if the electron absorbs energy, it's going to move in a way that correlates with how much energy it absorbed. So we call this excited state. Okay, ground state, which is this first image, is the expected electron arrangement. Okay, neon has 10 electrons. There would be 2 on the first ring, 8 on the second ring. Everybody's where it's supposed to be. But if I zap the outside of this electron with some kind of high energy wave, like an X-ray or heat or ultraviolet light or something like that, if an electron gets exposed to that, it's going to jump up to an energy level that correlates with the amount of energy that it absorbed. Consequently, if the electron then releases that energy to go back to its original energy level, it's going to have to let go of the same amount of energy that it absorbed. And you have a reference sheet where you can check and see what kind of wavelength of light an electron is going to release if it's transitioning from an excited state to a ground state. So if we're looking at this diagram, for example, and you're told that an excited electron moves from 6 to 3, okay, what you need to look for on this reference sheet right here is where the electron is currently on level 6 and demonstrating that it is going to move to level 3. So if you move through the examples, okay, this dot is on 6, but it moves to level 2, so that's not our answer, so we're going to keep going to this one. Okay, here we see a line that represents a transition of 6 to 3. So that means the wavelength of a photon that's going to come off of this electron is 1094, okay, and then the unit is nanometers. If we're looking for the wavelength of a wave that goes from 4 to 1, we need to find the dot on 4 that points at level 1. So we're going to move level 4. Okay, right here's a level 4, and this is the one that goes to level 1. So that means that we have a 97 nanometer photon. Okay, and then right below it, you'll see UV. So that lets you know that that's an ultraviolet photon. If an electron releases a photon of visible light, you can be asked for a little bit more information, which is color. So if an electron transitions from N5 to N2, okay, we're going to move 5, down here. Okay, that's going to be this photon right here. So we're looking at 434 nanometers. So that tells you that it's visible on the top, but it doesn't tell you color. Okay, what we need to look at is the bottom of your periodic table where you have the electromagnetic spectrum. Okay, 434 nanometers. That doesn't look like a nanometer. NM. Okay, is the same thing as 4.34 times 10 to the negative 7 regular meters. So 434 is going to fall in between 490 and 420. So that means the color of that photon is going to be blue light. So our last example, if we have a photon that goes from 3 to 2, okay, that's going to be this one, which is 656. So if I check my reference sheet, okay, 656 falls right here in between 650 and 700, so that means it's going to be red light.